Hello everyone, this is Kevin Lin, and today I'll be covering the content of the Module 3. So let's get started. Okay, so in today's presentation, I will be talking about three aspects. And the first one, I'll be talking about the general linear model. It's as known as the GLM. And then I'll be talking about two models, and the two models is within the general linear model. And the first one is MRC. It's multiple regression and correlation. And next one is ANOVA. It's analysis of variance. Okay, to begin with, let's talk about the general linear model. So the linear here, it doesn't mean that it's rectilinear. It just simply means that the element of the equation is additive. So here you can see the equation is y equals b0 plus bx plus e. And y here is the dependent variable. And the b0 is the intercept. It serves as the best guess when there's no predictor. And the b is the weight assigned to the predictor. And x is predictor. And e is residual. There are several assumptions within the general linear model. So here I list some of them. And the first one is linearity. Linearity means that, so as I mentioned before, everything is additive. And the second one is random. So it simply means that you should sample your data randomly. And non-collinearity. This one means that the predictors shouldn't be correlated with each other. Okay, so the next one is exogeneity. It means that the predictors is uncorrelated with error term. So there's actually some limitation of the predictors in the general linear model. Okay, and the next one is the homoscedasticity. It simply means the error of the variance is constant. It's kind of vague, but I think it'll be better explained when we see the scatter plot. So for now, let's move on to the next page. Okay, so here's the data. Excuse me, I cannot put all of the 30 rows in one slide. So here I show you the first 10 of the 30 rows. And the Y1 to Y4, they serve as the dependent variable. And the X1 to X7, they are predictors, but I won't be using all of them. And there are 8 factors, and I will be using them when I talk about the ANOVA. Okay, so the MRC. So in this model, in this MRC model, I'll use the X1 to predict the Y1. And here's the outcome. The outcome is generated by the R. So let's take a look at the X1 here. So the value here is the 0.4, and the estimate intercept is almost zero. So it's minus 0.002. It's very small. You can just take it as the zero. Okay, and with those two values, we can write down the equations. So y equals 0.4, x1 minus almost zero. So how about the values over there? So the t value here is simply you use this data here and to divide it by the standard error, and you'll get the t value. So also if you divide if the 0.4 divided by the standard error, the 0.11, so it will get the t value. And then to look up for the critical p-value, you'll get that it's below the 0.05. Okay. The next one, so if I use the x3 as a predictor to predict the y1, also you can see here, so I won't be repeating myself, but here is the b. So the estimate x3 value is serves as a b. So put it right here in the equation, and the intercept here is you can put it in the equation here. And if you put this value and divide it by standard error, you'll get the t-value. So this is more important than intercept. This one is more important. So as you can see, it's also below the critical p-value. Okay, but now if I put x1 and x3 together to predict the y1, something's different. So here you can see that there's x1, x3, and the interaction of x1 and x3. So yeah, they are only x1 is below the critical p-value, and the rest of the data is not. So let's take a look at some other data. So here I show you the VIF. VIF is the variance inflation factors. So it's just you can use this value to determine whether your predictor is inflated or not. So if the amount of the number is 1, it means that it is not inflated. But if it is over 1, like here x1 is 1.8, it's almost 2, and also x3 is 1.9, it's almost 2. So it's like twice the time of the it is inflated like twice of the time. Yeah. So but 2 is not like it's not like a value you should be aware of. So there's no critical value, but the higher the value is, the more inflation the predictor is. So I mean, the lower the better. So it should be like 1 is the best. Okay, so let's move on to the next page, and there's scatter plots of the first one is the plot of the residuals. So it's better that the residuals has no like no inclination to one side or another, and the line here it's better horizontal, so it looks pretty good, and the data is like scattering, it's not like centered to somewhere, so it's good. And here's the QQ plot, and you can see whether it is normal or not. So it looks pretty good. It's along the line, so it's not like looking like an S shape or something. So it looks pretty good. And here you can see the third plot is that if there is like homoscedasticity, and it should be like looking like this or looking like this, but it looks pretty normal. So there's some data right here. So, but I would say the homoscedasticity is not very bad, not bad. And the final plot is the goal of the final plot is to see if there is outliers. So the quick distance, if there is one data that is located like here, then it will be viewed as an influential outliers. But seems that there's no data over the quick distance. But here you should note you should be noted that according to Cordner, he says that if you want to like get rid of your outliers, you should you should have sound understanding of your outliers, because like there are many kinds of outliers, and for example, there's at least four kinds of the outliers. Some outliers are like data point based, or some outliers are study based, or some outliers are variable based or case based. So there are different kinds of outliers. So before you want to get rid of the outliers, you should know that what kind of outliers you are dealing with. Okay, so here we're only discussing the unstandardized regressions, but like according to Gary King, he says that the regression is simply a sample estimate of a conditional expected value. And he also says that unstandardized regression coefficient is like a better options because it has more information comparing to the standardized regression. Okay, so let's move on to the ANOVA. So ANOVA, there is a slightly difference between the regression ANOVA and ANOVA. So ANOVA, we use factors instead of the predictors. So here we use factor 4 and factor 6 to factor 4 and factor 6, and this is the interaction of the two. And here's the residuals. So the sums of the square is some other form of the variance. So and the mean of the sum of the squares is simply you use this data and divide it by the degrees of freedoms, and you'll get this value. And then if you and the f value, if you this is like the between group variance, and the residual is the within group variance. So if you divide it, if the 0.117 divided by the within group, the between group divided by within group, you'll get a p-value. And using this p-value, you can find the p-value, critical p-value. Okay. Also, we can draw a plot, and the residuals here. You can see that there are different residuals right here, and here's the normal distribution of the data, and they kind of a little bit deviate from this line, but it's not very dramatically. So, and given this data is only 30, is a small amount of data, so it's not very bad. The next one is the you can this data, we use this data to see if there is heteroscedasticity. So I think it is not our biggest concern. So let's move on to the next one. And the Cook's distance. So yeah, there's no data. I think there's no like dramatic outliers here. So okay. And this is my handwriting of the MRC and ANOVA. And thank you for listening, and hope you have a great day. Thank you.